Everyone, thank you for being here today. I'm Abby White, the Project Manager and Structural Engineer for OKAE Engineering. With me today, we have Katie Schreiner, our Transportation Engineer, Ellie McCullough, our Waters Resource Engineer, and Olivia Holtz, our Environmental Engineer. And today, we're excited to present our final presentation for the Amazon Industrial Park project located in Elkhart County. Specifically, the project is located between County Road 17 and County Road 19, and just north of the Indiana Toll Road. And it includes the design of a warehouse facility, a wastewater treatment facility, a new connector road, as well as the implementation of stormwater management practices. And you can see an image here. This is the project site limits with the existing conditions, and this is the project site limits with our proposed design locations. As project engineer, I've overseen the coordination across all engineering disciplines, but today I'd like to focus solely on the structural portion of the design, the warehouse. As a reminder, the warehouse is a one-story steel structure of approximately 48,000 square feet and will include spaces for office and reception use, equipment storage, warehouse storage, packing and shipping areas, as well as auxiliary spaces. And this is just a brief outlook at the warehouse roof steel framing plan. It's located within the red. And this is the office roof steel framing plan. These are different slides as they're set at different elevations. And so let's take a look at the gravity system design. This design consists of the beams and girders that are in the framing plan. One thing that is important to note here, and you may be wondering why there's a drastic difference between the two different sizes of the office and warehouse beams and girders. And this is due to the applied loadings on the structure. So there's an elevation change, as I mentioned previously, of about 15 feet from the warehouse and the office. And this requires in the office that this will increase the snow load drift in the office, as it just not only has the flat snow load that would be in the warehouse, but it also includes the snow drift load, which increases the load drastically according to ASC 716. This means that the members in the gravity system design needs to be larger in the office to be able to use this loading. And another thing that's important to note is that the members that are in red, those are the ones in the moment frame. Now taking a look at the column design, here it is important to note that the columns sizes will vary based on the location of the columns as well as the loadings applied, like I previously talked. Taking a look at both of these images, the columns outlined in blue are the columns in the moment frames, and the columns outlined in yellow and red are the typical columns found in the warehouse and office that are not in the moment frames. And the variation is due to the location and the load is applied. Now taking a look at the lateral system design. This design consists of a hybrid system of moment frames and brace frames. The brace frames are steel channels of C10 by 30, where the moment frames consist of beams of W21 by 201 and columns of W24 by 162. We include both of these brace and moment frames due to it's providing extra strength to the structure, as the brace elements provide stiffness to reduce any drift, and the moment frames provide ductility between the columns and beams as they are able to resist lateral loads through flexure. And like I said, having these combined helps provide the stability and structure of the strength of the structure. And here are the north and south elevation views. These are the walls that have the brace frames, as you can see here. One important thing to note is that there is an elevation change, like I mentioned, and you can see that here where the elevation changes from 35 to 20. You'll see these in other slides. And here are the east and west elevation views. These are the outer ring walls. And here are the office walls elevation views. One thing that's important about this slide is that these are the walls that kind of connect the warehouse and office, so they require kind of like a double type of beams in here if so to say, and it's because you need a beam at the office level as well as the warehouse level. And here are typical section elevation views, where these are just like if you were just sitting in the structure. These are large open spans so that any warehouse storage or just any equipment can get around. Now looking at the slab design, this is the bird's eye view of the slab. And the slab is a concrete slab on grade with number 7 bars sitting at 9-inch spacing. The material is just a close-up view of the slab. One thing important to note is that the steel reinforcement is a 2-layer rebar with laying perpendicular to each other. To be able to design this slab, we assumed the largest occupancy load on the slab, which would be a heavy storage warehouse, is what is highlighted in red. I know it requires that means that this is a huge over-design for some portions of the site, but I wanted to make sure that the slab could withstand any of the loads in any part of the building without breaking. Now moving on to the partial construction cost estimate. The reason why this is a partial construction cost estimate is because it only includes the structural framework layout. It does not include any of the fancy things such as drywall, walls, lights, all that type of thing. And so I used RS-Means line item estimator for this. And that being said, it comes to a total of about $2.4 million with a 20% contingency cost. And now that concludes the structural portion of this presentation, and now I'd like to pass it on to Katie.
Hi everyone, as Abby mentioned, my name is Katie and I'm the transportation engineer with OKAE Engineering. I was tasked with the design of the County Road 4 extension going from County Road 17 to County Road 19, as well as the development of any parking structures related to the site. These items are to be designed in accordance with the Indiana Design Manual, the AASHTO Green Book, Elkhart County Codes and Regulations, and the Americans with Disabilities Act. Pictured here is the chosen roadway alignment for County Road 4. This lines up really well with the existing infrastructure on the east and west end of the site, and it's also far enough south from the wetlands on the north half of the site to allow for future developments on either side of the roadway. This alignment also resulted in a slight realignment of the Indiana Toll Road entrance, but is a very minor adjustment. The County Road 4 extension has a design speed of 45 miles an hour with 2 travel lanes, 1 lane in each direction. One thing that's interesting to note about this alignment is we chose to use the low-speed urban cables for the horizontal curve design rather than the standard design curve cable. This is to keep speeds low since there's going to be a high amount of heavy vehicle traffic on the site. Pictured here is the typical section for County Road 4. As you can see, there's those 2 travel lanes that are 12 feet wide, 1 in each direction, as well as a 10-foot shoulder on either side of the road. This shoulder has a 6-foot paved section and a 4-foot unpaved section. You will also notice that this cross-section is crowned, and that is to facilitate drainage to either one of the vegetative swales along the road, which our water resources engineer will touch briefly in a minute. Looking at intersection design, this roadway resulted in the design of 2 new intersections, the first of which is between County Road 4 and the Indiana Toll Road entrance. This will be a signalized intersection. The major movement at this intersection is between the southbound County Road 4 leg and the northbound Indiana Toll Road entrance, which resulted in 2 right turn lanes going from the County Road 4 leg to the Indiana Toll Road leg, and 2 left turn lanes going from the Indiana Toll Road entrance to the County Road 4. The second intersection is between County Road 4 and County Road 19. This is a stop-controlled intersection, with County Road 4 being a side street stop toward County Road 19. Now, both of these intersections were designed with the design vehicle of a WV67 and will have turning radiuses of 125. This roadway alignment is estimated to cost $4.2 million. This includes items such as traffic control devices, pavement costs, and striping, as well as a 20% contingency included in that $4.2 million. Moving on to site design, there are 2 parking lots located on the warehouse site. one to the south side for cars and one to the north for trucks and heavy vehicles. The car parking lot will have 35 car stalls and 4 handicap stalls, and the truck parking lot will have 30 car stalls and 6 loading and unloading bays. Getting a closer look at the parking layout, the car stalls will be 10 feet by 20 feet, and the truck stalls will be 12 feet by 80 feet to accommodate that larger vehicle size. It's also important to note the traffic control on the site, since there are 2 driveways. The driveway on the eastern side of the site is a enter-only driveway, and the driveway on the west half is a exit-only. This is to reduce the conflicting movements coming on and off the site, since there will be lots of heavy vehicles. The cost estimate for this parking lot is $1.4 million. Now this is higher than what was originally estimated, since we decided to go with a permeable pavement option on the actual parking stalls in both parking lots, which ended up raising the price, and this also includes the pavement and striping design as well, and that 20% contingency. At this time, I'd like to pass it off to our water resources engineer.
Thank you. Good morning. As mentioned, my name is Ellie, and I'm the water resources engineer for this project. First, I want to go over the key components of the water resources project. We will be managing the stormwater runoff from the site primarily by controlling flooding and reducing or treating the stormwater to improve stormwater quality. This specifically will result in a retention of at least 80% of all total solids and 65% of all total phosphorus. Here we have our selected design alternative. This is a series of best management practices, or BMPs. We have a detention pond for storage and infiltration, vegetative swales for conveyance, permeable pavement for infiltration, a rain garden for infiltration and pollutant removal, and then finally a sand filter primarily for pollutant removal. As you can see here, we have the project layout, or the site layout, that shows the stormwater flow throughout the site. We have the runoff coming from the impervious surfaces, primarily the warehouse facility and the new road, moving into the vegetative swales to be conveyed. Then it enters a series of stormwater BMPs, either coming off of that permeable pavement parking lot, or the roadway vegetative swales, and then going into first the rain garden, then the iron enhanced sand filter, and then finally settling in the detention pond before outletting into the wetlands. Getting into the specifics of the best management practices, first we have the vegetative swales. In this project we have 2 different types of vegetative swales. The first is a standard grass swale that will be used along most of the roadway. It can be seen here on this image, and it has a 4-foot bottom with 3-to-1 side slopes for a total of 16 feet of width. This is a standard grass swale, as mentioned, and will have a 3-inch topsoil. And then the other type of swale we have is what we call an infiltration swale. This will specifically be used on site around the facility, the warehouse facility and development. It is a little bit different and used to support further infiltration than the other types of swales, and it has a 3-inch engineered media layer and a 3-inch pea gravel layer to support that infiltration. Next we have a rain garden. This is a rectangular basin garden with increased vegetation. It's designed to have a 1.5 foot ponding depth with an additional 1.5 foot of freeboard. It has a length to width ratio of 3-to-1 and side slopes of 4-to-1, resulting in a 90 by 270 foot garden with that 3-foot total depth. For the media used in this rain garden, we really want to prioritize not only settling solids, but also taking out some of that phosphorus. So we are using a media and vegetation design that prioritizes phosphorus and preventing phosphorus leaching, and therefore it has as low of an organic matter as possible. Next we have a sand filter. This is, as mentioned, an iron enhanced sand filter. It is also a rectangular bed, as with the rain garden. As you can see here, we have a 3-to-1 length ratio with the sides and 3-to-1 side slopes. And then this will have an outlet height of 4 feet from the sand media. And then that will result in a 50 by 150 foot sand bed with a total of 7,500 square foot in the bed. The sand filter is primarily used for getting out some of our dissolved phosphorus, as the rest of the phosphorus can be a little bit easier to remove as it is particulate and settles out. Dissolved phosphorus tends to be the tricky part within this project. Therefore, our iron enhanced sand filter will specifically target that phosphorus. Next, we have the permeable pavement, as Katie mentioned earlier. This will be, again, only in the parking stalls, so only where you see the little tiny parking stalls on this image. And however, the subsurface reservoir will extend beyond the stalls and go across the entire parking lot. That will result in a total of 1 foot and 2 inch depth for that subsurface reservoir in order to contain the entirety of our water quality volume from the building and parking lot only. That's at almost 15,000 cubic feet. And that also allows for 50% void space within that subsurface reservoir. Finally, we have a detention pond. This has an assumed 2-to-1 length to width ratio with a rectangular bed along with 3-to-1 side slopes. The outlet of this structure, or the outlet of this BMP, has a 5 feet depth from the bottom of the basin, resulting in a 41,500 square foot pond. This has also been designed to meet all hydraulic requirements using TR55 for the inflow and double pull routing for the outflow, resulting in a maximum drain time of 32 hours with our design storm of the 100-year, 24-hour storm. Finally, we have our partial construction cost estimate. These are based off of the size of these stormwater BMPs, primarily from the US EPA, and that results in about an $800,000 total cost with our 20% contingency. Thank you, and I'd like to pass it off to Olivia. Thanks, Lauren.
Good morning, everybody. As mentioned, my name is Olivia, and I'm the environmental team lead for OKAE Engineering. My portion of this project included designing a wastewater treatment facility designed to manage an average flow daily of 1 million gallons per day. So this would include designing for the pre-treatment, primary treatment, biological treatment, and any secondary treatment as well. Due to the location of our wastewater treatment facility and our site, it is in Elkhart County, which means I had to follow any rules and ordinances from Elkhart County, from the Indiana Department of Environmental Management, or any National Pollutant Discharge Elimination System permits that fall under the Clean Water Act of the Environmental Protection Agency. So as you can see here, this is the typical treatment train schematic for a wastewater treatment facility, and these are actually all of the components that I used for my treatment train. So the bar racks, partial flume, and aerated grit chamber are all included in the pre-treatment. The primary clarifier is used for the primary treatment. Activated sludge is our chosen biological treatment alternative. And then the secondary clarifier, filtration, and disinfection are all used for the secondary treatment. So I already touched on these first three a little bit, but I'll just do a little recap. So the partial flume design has a throat width of 0.3 meters, and then the plume depth is going to be a total of 0.82 meters. And this is just a schematic of what it would look like with all the given dimensions. The bar racks, there will be 23 bars with then 22 bar spaces. The effective area based on our flow will be 0.306 meters squared. The velocity through it will be 0.638 meters per second. And just as a note, to prevent any damage to the bar racks, it must be less than 0.9 meters per second. And then the head loss when it's clean will be 24.79 millimeters. And then we practice for a clog of some sort that would be preventing like 50% of the flow to go through. And just to make sure that these bar racks would be able to handle it, the head loss for that when it's like 50% clogged would be about 110.19 millimeters. And head loss is limited to 150 millimeters, so even when it's clogged, we're in pretty good shape. Otherwise, we've got the aerated grit chamber, and the complete volume of the chamber will be 35.5 meters cubed, with a depth of 2 meters, a width of 2.5 meters, and a length of 7.1 meters as well. The velocity through the bottom is going to be 0.15 meters per second, and this is just to make sure that everything settles without just getting completely mixed again. Now onto some new stuff. So for the primary clarifier, this is again for the primary sedimentation. And we use type 1, which is discrete settling, and this means that the particles will settle independently. And as you can see from the image here, there is the splitter box in the middle and the two clarifiers on the end. As you might be able to assume, a splitter box just means that it splits the flow between the two clarifiers, just making sure that this is managed easily. And due to the size of our wastewater treatment facility and the average flow, we just needed 2 primary clarifiers for this, so it made my life a little bit easier. That being said, the depth of the box below is about 2 meters, 2.5 meters or so. And then the diameter of each of the tanks was calculated to be 12.67, but then just for like normal values and like a little bit of extra precaution, it was rounded out to then 15 meters per diameter for each of the clarifiers, just to make it a little bit safer. And then as mentioned, 2 clarifiers were used based on the size of our flow. Next for activated sludge, which is the heart of biological treatment. As mentioned last semester, activated sludge was the design alternative that I was determined to be the best. And so the mean cell residence time will be 6.2 days, and the hydraulic detention time will be 0.344 days, which is roughly about 8 and some change hours. And then the volume will be 1,302 meters cubed per tank. And this is, again, you need 2 tanks for sure, and then we added a 3rd one just for redundancy purposes. So the net waste of activated sludge produced was 420 kilograms per day of volatile suspended solids. And then the number of aerators required was calculated to be 272 aerators. Seems like a little bit much, but based on the size and the flow, we're about there. And then this is just a diagram of what the influent into the aerator tank looks like, and then it goes on to the secondary clarifier. And then for our process, the activated sludge gets discharged from the secondary clarifier and can either be returned to go through the process again as return activated sludge or otherwise out as waste activated sludge. Speaking of the secondary clarifier, it is going to be very similar to the primary clarifier. This is just going to make sure that the rest gets all kind of settled out and that we're all good to go. Clean up any pollutants and anything that we're kind of worried about. So again, the diameter was 12.67, rounded up to 15 for each of these. And the flow rate for the return activated sludge was 2,271 meters cubed per day. And the flow rate for the waste activated sludge was just about 100 meters cubed per day. Again, 2 clarifiers were used. And for this sedimentation, this would be type 2, as it is flocculent settling, which means that particles will flocculate as it settles. And then the mass wasted is going to be 600.6 kilograms per day, roughly. The final stage would then be filtration and disinfection. So for filtration, we decided to use a cloth media filter. The area of each filter is going to be that flow rate divided by what the loading rate is. And the loading rate was about 5 meters squared per meter cube per day. It's really weird units for some reason. And that gives you about an area of 141.94 meters squared. And then based on that, we just need 3 filter units. It was a little bit more than 2, so then we just added on a 3rd one again for redundancy purposes, just to be safe. And then the real loading rate is going to be 5.07 meters cubed per meter squared per hour. And then the great thing about cloth media filters is that they actually do a pretty great job of this final filtration. So the expected effluent discharge then will have about a little bit less than 5 to 10 milligrams per liter of total suspended solids, turbidity of less than 2 NTU, UBT of 65 to 70%, and then BOD5 of less than 25 milligrams per liter. And the standards in the area are actually for 30 milligrams per liter, but just to be a little bit more stringent and play it on the safe side, get a little bit of cushion room, we did design for an effluent of 25 milligrams per liter. And then lastly, we got the disinfection process used was UV disinfection, because it's pretty great at disinfecting. It's one of the higher industry ones. And the exposure time will be about 8 seconds for all of the water to be exposed to UV. And then the reactor volume required is 1.58 meters cubed. And the dimensions of the channel can be seen there as well. And then in total, based on all the calculations, we need 54 lamps for the UV disinfection. And then finally, we've got the partial construction cost estimate for the treatment facility. And as you can see, some of these we need to add a couple tanks and items for redundancy, which I made a little note on the side. And then for a total construction cost estimate of about $16.4 million. And then with a 20% contingency, it comes out to be about 19.6. And then that concludes the environmental portion, and I'd like to pass it back to our project manager.
Thanks, Olivia. Looking at all the different components of our design, we've come to a total estimated of the construction cost being about $33.5 million, and this includes a 20% contingency fee. With this being said, this concludes our presentation. Thank you for letting us present today, and now we'd like to open the floor to any questions anyone may have. Professor Elgin.
So, maybe starting with you, Abby, since there on the structural part, and there, do you know what type of walls you would have for the structure?
Yes, it's DM40, the masonry wall panels. Those are standard for an Amazon warehouse facility.
And how thick is the wall going to be?
I'm unsure at this time.
Well, the reason I'm asking because you showed the column to me like 24 inches. I don't think the architect will like that. So if you're having like columns either sticking out or into the building because of the thickness of that. And that's why I'm asking about the thickness of the walls. So architects would like to hide the columns inside the walls.
Well, unfortunately, I'm an engineer, not an architect, so that would require further discussion.
You will be working with the architects for if you are a structural engineer. Okay, so my next question for you, Abby. So what makes a frame a moment frame? When you say a moment frame?
So it's the connection base of it. It's a rigid type of connection, and it allows, I can see the light keeps going in my eyes. It's a rigid connection, so it allows for the ability for the moment to be able to resist it with the lateral loads through flexure.
So what's the difference between a rigid connection compared to like a regular normal connection?
So a regular normal connection is pretty stiff. It doesn't allow for any movement, where the moment frame might have a little bit of some movement.
Really? It's the other way around, isn't it?
I would have to look into my notes further.
So how did you arrive at the snow drifting loading?
I used CEE 716. There's a process there. Unfortunately, I don't have the exact calculations with me, but it required adding an additional load based on the different elevation changes between the office height and the warehouse height.
Well, it seems to be a bit high, like over 100 pounds per square foot compared to maybe about 40 on using the HAS calculator.
I know, that was interesting. When I finished my calculations, I think I did them about 10 times because I thought it was a little bit crazy. And then double checked with my advisor about 10 times, still thinking I was crazy. But yeah, it ended up being a little high, but I was able to design the warehouse and office to be able to withstand that load.
I know I'm harsh, but you did a good job. So, okay, Katie, it's your turn now. Can you show me a profile of the road, please?
Yes.
No, I need a profile of the center line of the road, not
I don't have an image of the elevation, but I can answer questions about it if you would
Okay,
like.
well, see, I'm connecting your profile with Ellie's runoff flow, because she showed the runoff coming from both sides, from the right and the left, towards so I did not know if that's actually in line with your profile of the road, if the topography of the slope of the road. And so did you guys coordinate? Is it coming down to the sort of where she located the rain gardens in there?
Yeah, it does. It comes, the low point is right to the west side of the project site. We worked together on this since there were issues with elevations here with it being super flat. So we did pay special attention to making sure that the water was going to get to where we wanted it to go.
A simple question in here. Where did you get your unit costs, at least for the parking lot?
The Indiana line item estimator, provided I had that.
Okay, and it seems to be a bit high cost for a parking lot.
It's because we have those permeable pavement areas as well. Just raising costs higher. I conferred with my advisor, trying to figure out numbers used for that asphalt design, and he thought this would be the most appropriate since we were both a little unsure of what the proper estimate would be for that.
I guess I have to trust both you and your advisor in this case in here.
So
What takes me,
we have limited time for questions, so can we give
okay, maybe I'll speed this up.
Well, no, I think somebody else should have.
Okay.
Yes, we got at least three other people and students and stuff, so
Okay.
does anybody have?
Where does, you're collecting water and you're treating it, and you're saying we're getting rid of the phosphorus. Where does the phosphorus go?
Yeah, so as I mentioned earlier, there's two different types of phosphorus. So there's the particulate phosphorus, and then there's the dissolved phosphorus. So particulate phosphorus settles out just like solids does, so it settles into the bottom of the basins. Then the particulate or the dissolved phosphorus, we expect a large portion of the part that's actually retained to be in the sand filter.
It just stays there forever? Is it?
It requires maintenance and operation, so sometimes you can replace the sand, you can mix it up. There's a few different ways that you can go through the process of removing that, but yes, essentially.
Since we're asking questions of the water resources and the iron sand filter, is there enough, did you look into the elevation drop? Because you had like a series from like rain garden to sand filter to, and all that requires elevation drop. So
Right, yes, it's not great. I did the best I could to make everything as shallow as possible to limit the amount of elevation drop with each of the stormwater VMPs, but this site is just really, really flat. So that's the reason that a lot of them are so close together, is so that we could get more elevation drop between the actual VMPs. But overall, it's really difficult because the.
But you're sure it can work?
Very. I think it does. It'll probably work,
Yeah.
And then your cost estimate in dollars, some of those EPA documents that you referenced, they're older, so did you adjust the cost to $20, $25?
I did not.
Okay, I do that. Do you have any questions, Alex?
Yeah, I have a question. Could you please go to slide number 15? Yeah, Abby, you mentioned that one of the reasons that in the office level you have larger size members, it's because of the snowdrift, which makes perfect sense. But am I right in this elevation, like line 9, the size of the beams are the same?
Yeah, so these are the moment frames. So on the east and west sides of the building, they use moment frames, so the beams will all be the same size as they were designed all together.
Even with the larger snowdrift on the...
Yes, because I designed the beams for using the office load, load on top of it to be able to withstand the entire the entire building, even though the warehouse might not need to have that much load on it.
Could it be also because this frame is the exterior frame and those beams doesn't get that much of snowdrift?
Yeah,
Yeah.
that is also a possibility.
The second question, you mentioned that this is like a friendly comment just to like a side dish. So you mentioned that your system is a hybrid system. It's actually not. Hybrid system when we have moment frame and braced frame in the same direction. We
Okay.
call it hybrid, which is has different requirements. But your system has braced frame in one side and moment frame in the perpendicular direction. Could you tell us why did you choose that system? Why didn't you choose moment frame in both directions or braced frame in both directions?
Well, thank you. I did not know that it was not a hybrid system, so that's important to know. So the reason why I chose it is because, let's say the brace frames part of it fails, the moment frames is able to keep the building standing and stable until we can come in with any form of repairs. With the combination of the two of them, it helps provide stability throughout the structure in case anything were to happen.
So if the moment frame is stronger, why did you choose moment frame in both directions?
Because moment frames are way more expensive, so the brace frames are a cost-effective approach to it. So the combination of the two was able to add the strength to it using moment frames, while also not increasing the cost.
Thank you.
Any other questions? Thank you.